Welcome back. Today I'll tell you the story of ortho, meta, and para directing effects in organic chemistry. These effects are in regards to electrophilic substitution reactions, which are reactions that are done to aromatic molecules such as benzene. By the end of this video, you'll know how to deal with directing effects in a reaction in which benzene already has one or more substituents. To understand these reactions, we need to have a good understanding of what ortho, meta, and para mean. These are going to be positions on the benzene ring, and in this case, as I have shown here on the screen, they're going to be in respect to the atom X, so some group. These are the ortho positions with respect to X, this is the para position with respect to X, and these are the meta positions with respect to X. So if X were to move, then you would reassign the ortho, meta, and para positions. Now let's talk about the next important concept, which is the difference between activators and deactivators. An activator is going to be a group that makes the aromatic ring react faster than it would have done alone. So it makes benzene react faster than benzene would have done alone. Now, characteristics of an activator include that it's going to be an electron donating group via resonance and induction. That means it's going to be giving electron density to the ring. In contrast, we have the deactivator, and it's going to be the opposite of an activator, which means that deactivators are going to be the type of molecule group that are going to make the benzene or aromatic ring react slower than it would have if it were alone. Now, characteristics of deactivating groups include that they are going to be electron withdrawing groups via resonance and induction. So that means it's going to take away electron density from the ring. Let's focus a little bit more on the reactions now. So here we have an electric substitution reaction with one substituent already on the ring. Now we have a few cases, a few possibilities that can occur depending on whether X is a halogen, whether it's an activator, or if it's a deactivator. Let's take those cases one by one. If X here is an ortho-para director, then the new group, the new substituent, is going to be placed at ortho-para positions. Things that direct new groups to ortho and para positions include activators and halogens. In another situation, if X is a deactivator, then the new group, the new substituent, is going to go bind to either of the meta positions. So meta directors, meaning groups that direct new groups to meta positions, are going to be your deactivators. Now watch out for halogens, because they are deactivators, but they are ortho-para directors. In other words, they are your exception. They're going to make benzene react slower than it would have alone, but halogens make other groups be added to the ortho-para sites. The reason why halogens behave this way is because they give electron density through resonance, but they take away electron density through induction. So remember, if you see a halogen on your aromatic ring, just remember that it's going to be a deactivator, but it's going to be ortho-para directing. Now at this point in the video, you might be asking yourself, how do I know which are the activators and which are the deactivators? Well, the good news here is that here is an order according to the strength of activation. On the internet, you can find a rich variety of resources like this, listing the activating and deactivating groups. On my website, I have a handout listing the activators and deactivators with their respective strengths. Another situation that could arise with these types of reactions is when you have two groups already on your benzene ring and you want to know where to place a third group. So for this situation, let's say that we have X and Y attached to the ring. And in this case, X represents one group and Y represents another group. For this situation, what you're going to do is you're going to find the most activating group bonded to the ring. So you're going to compare X and Y and decide which one is the most activating group. Once you have found your most activating group on the ring, that is going to serve as your reference point for your ortho, meta, and para positions. Remember, in the beginning, we talked about how ortho, meta, and para positions can vary depending on where your molecule group X is. And so in this case, once you have found your most activating group, that is going to serve as your reference point in order to place the ortho, meta, and para positions. Another note here for situations with more than one substituent on the ring is going to be that places that already have a substituent will usually not gain a new group. They're going to stay the same. That means that if you are going to add to the meta positions, but one of your meta sites already is taken up by the other substituent, then you will only add the new group to one of the meta positions and not the other because the other is already taken up. Likewise, if your reference point is an ortho-para director, but one of those positions, ortho or para, is already taken up by the other group, then you will not add a new group to those sites and instead just add it to the sites that are left over, that are available. Another consideration for placing an additional group on a ring with two substituents or more is that you want to take sterics into account. And preferably, you're going to probably want to place the new group where it's less sterically hindered. In order to demonstrate how ortho, para, and meta directors work, let's try some examples. Now, given this example, what would you write for the final product? This is going to be an electrophilic aromatic substitution, and looking at these things on the arrow, we know that these reagents point to a halogenation. Halogenation in this case means that somewhere on this benzene ring, we are going to replace one of the hydrogens with the chlorine. The question, of course, is where do we do that? To place chlorine in the correct location, we're going to take a look at the OH group. The OH group is an activator. This means that the OH group is going to direct new groups to the ortho and para positions. One of the products is going to have chlorine in the ortho position, and another product is going to have chlorine in the para position. One of the products we can write is chlorine in the para position. Remember, this is going to be para with respect to our activator. The other product is when chlorine is going to be directed to an ortho position. Now, these are the two ortho positions. And because this is symmetrical, it doesn't really matter which ortho position we choose, they're both going to be the same product. So for example, we can choose to write chlorine up here at this ortho position. And so you have your two products. Now try this problem on your own and see what the final product is. Looking at this arrow, we immediately see there are going to be two parts to this reaction. In the first part, we're going to react the fuming sulfuric acid, and in the second part, we're going to do another halogenation, this time with bromine. The first reaction is a sulfonation, which means somewhere on this benzene ring, we should be adding this group, right? Substituting in this SO3H for one of the hydrogens on this group, one of the hydrogens that's connected to this benzene ring. So the question is, where should we do that? To decide where we're going to place SO3H, we're going to look at the substituent that's already on the benzene ring. And if you look at this, you're going to see that this is a deactivator. These meta positions are in respect to this substituent here, which is our deactivator. This is going to be a symmetrical case, and so placing the SO3H at either the top or the bottom meta position is the same product. I'm going to choose to place the SO3H at the top meta position. Now we have the second part of our reaction, the halogenation. Now this halogenation is going to replace one of the hydrogens on the benzene ring with a bromine atom. And the question is, where should we place this bromine atom? Now our end product is going to end up having three substituents. Both of these groups on the benzene ring are deactivators. And so we have to figure out, well, which meta positions do we choose with respect to which group? We are going to compare these two groups. And when we do, we're going to figure out that this one is more deactivating and this one over here is going to be more activating. They're very close to one another. They're both deactivators, but this one here on the bottom is going to be slightly more activating. And so we are going to choose our meta positions with respect to this more activating group. The only meta position left is this one right here, and so this is where we will place our bromine atom. And so we have our final product of this reaction. Here is another example. We have two substituents, and on our arrow we have the reagents for a nitration, which means somewhere on this benzene ring, we are going to replace one of the hydrogen atoms with NO2. Given that this ring has multiple substituents, our question is, well, where do we place the NO2? Because the ring has more than one substituent, we need to compare these two groups and see which one is more activating. Doing this, you're going to see that the NH2 is going to be far more activating than the fluorine. And so we're going to use the NH2 group as our reference point. From here, we're going to designate ortho and para, because NH2 is an activating group. Our ortho positions are going to be here in these blue spots, and our para position is going to be in this red spot. So we're going to have two possible products. One is when the NO2 is added to the para position. And our other product is when the NO2 is added to either of these ortho positions. Now, because you have more than one substituent on the ring already, this is not exactly symmetrical. And so whether you add the NO2 to the left or right ortho position, those are going to look like slightly different products. So in one case, we can choose to place the NO2 to the left, and in another case, we can choose to place it on the right. And so here are your possible products for this reaction. That's the end of this video. I hope you enjoyed it. There is a link down below to access science and math tutoring, my website and free resources, and my publications. Thank you so much for watching, and I will see you next time.